So today's notes, we're going to talk about properties of definite integrals. And a reminder, definite integrals are integrals with with endpoints. So from some a to b. So these are going to be some rules, some properties that just kind of help us, some shortcuts. The first one is if our limits are the same, like the integral from a to a of f of x dx, that's going to be 0. One thing I do want to talk about is just how we say these, how we write these and read these is the integral from a to b of f of x dx. Okay, you may want to write that down like when we're reading it or we're saying it out loud. We say that this would be the integral from a to b of f of x. And then you can say like, dx. And then the reminder being that what that represents graphically is if we have an a and we have a b, graphically that's the area under the curve from a to b. So maybe that graph keeps going, but it's that area from a to b. So that's why we say the integral from a to b. So if instead we had the integral from a to a, then it's 0. And the reason it's 0 is, graphically on that one, if you did the area, it's just a straight line, and a straight line has no width, right? The area of a rectangle, like the Riemann sums we did width times height. This has no width. Okay, also if you did the whole like FTC, fundamental theorem of calculus, so we did it like from 3 to 3 of f prime of x dx, the integral of f prime of x would be f of x. From 3 to 3, you plug in f of 3 minus f of 3, you're going to get 0. So you don't need to show any of that work ever. Just if you ever see that two endpoints are the same, you can just jump straight to 0. Okay, our next one is the integral from a to b is going to be equal to this kind of addition problem, but I want to write it a little bit differently. So let's actually cross this out, and let's write it as the integral from a to c of f of x dx plus the integral from c to b of f of x dx is going to be equal to the integral from a to b of f of x dx. And so graphically what this looks like, they're saying we have some new value c in the middle. So if I put some c in the middle here, now this first integral is the integral from a to c. So the integral from a to c, that would be this left side. And then plus the integral from c to b. So from c to b, that would be that right side. And that should be equal to the overall integral from a to b. That makes sense when we look at it with the graph. Okay, and when we're looking at it on questions, sometimes they won't give you a graph, and instead they'll say something like this. The integral from, say, 2 to 6 of f of x dx, they say is equal to like 4. And the integral from 6 to 8 of f of x dx is equal to 5. And then they want to know what is the integral from 2 to 8 of f of x dx. And so what you'll kind of see is that 2 is our starting limit, and it's our starting limit. 8 is our ending limit, and it's our ending limit. And then 6 is in the middle both times. And so that kind of almost like cancels out. Like we're going from 2 to 6, and then again from 6 to 8. That's the same as going from 2 to 8. So we just add those up, and we get 9. So that's kind of how that works. Now, it will get a little bit more complicated with that, because sometimes you'll have to flip some integrals and do some negatives, and that's what we're going to get into here. So rules 3 and 4 kind of are almost the same rule. And so that's the integral from a to b of f of x dx. If we flip our endpoints, then the answer, k is just some number. It could have been 10. If we flip our endpoints, the answer will be negative k. So like if our integral was equal to 10, now it's equal to negative 10 when we flip the endpoints. And rule 4 is kind of the same thing, just showing that if you flip the endpoints, that integral turns negative. And so kind of what this is going to show is that so far what we learned is if we had an integral that had an area under the curve, right? We said that that area under the curve was negative, and the area above the curve we said was positive, right? Well, there is another case where we can get a negative answer, and that's if our endpoints are going backwards. So say like from 2 to 3, if we had some integral, right, from 2 to 3, And maybe we know that the integral from 2 to 3 of f of x is equal to 4, right? That's reading left to right. Now, if instead we said, what is the integral from 3 to 2 of f of x dx? Well, it's the same area, right? But now we're going right to left. And so kind of thinking like with the Riemann sums, like the width times the height, that width is going to be negative because we're going backwards. So it's going to be negative 4. So instead of it being positive 4, it's negative 4. So what we want to remember is anytime you flip the endpoints, that integral switches signs. This works too, like if we're going backwards in this negative area, now it would be like a double negative and it would have turned positive below the axis. Okay, our next rule is the constant rule. And that's if we have some k being a constant, you can actually just take that k and pull it outside of the integral if it's being multiplied. So this would be k times the integral from a to b of f of x dx. You don't have to do this, but you can do it. This kind of, we've done some integrals where like, so we did the integral of 2x dx, right? And we kind of said that that's 2x squared over 2, and the coefficient's just kind of hanging out. But you also could have pulled out the 2 and said 2 times x squared over 2. The 2 still cancel, it's the same thing. So this rule is just kind of telling us that any constants, any coefficients, they just kind of hang out, they remain there. And if you want to even pull them outside of the integral, you can. Okay, rule 6. Again, we've already actually really done this, but rule 6 just says any plus and minus signs, I like to think of them as kind of separators. And so we can even separate the integral. So we can say this is the same as the integral from a to b of f of x dx, and then plus or minus the integral of g of x from a to b dx. And so this is basically just saying that we can separate our integrals if we need to. And we've basically already done this again. Like we've done questions where we have 2x plus 3 dx, and we haven't really had to write this way, but we've just done them separately, like 2x squared over 2 plus 3x plus c. This is just showing us that if we wanted to, we could write this as the integral of 2x dx plus the integral of 3 dx, and we would end up with the same answer. So most of the time, rules 5 and 6 aren't really that important. So the rules that are really the most important are rules 1, 2, and then 3 and 4, kind of like I said, the same rule. And those are 3 most important rules. 5 and 6, honestly, most of the time we just do without thinking about them. Then rules 7 and 8 are not necessary. You're never going to need them, but they're just kind of shortcuts that can help you out. So if f of x is an even function, remember even function is y-axis symmetry. That's what we know about even functions. And so then the integral from negative a to positive a is going to be equal to 2 times the integral from 0 to a of f of x dx, or we can do 2 times the integral from negative a to 0 of f of x dx. And so graphically, kind of if we had like negative a and positive a, you can see that because of this symmetry, right, those two areas are going to be equal. So you could either do, the left integral, which would be that bottom one, and then just double it, or you could have done the right integral, which is that top one, and just double it, and that would be the same as the overall. So again, this is something that you're never going to have to do, but it could help you out as a shortcut to save you some time if you notice that symmetry. And then similarly, if we have an odd function, that's going to be like our our origin symmetry. So if we have an odd function, then the integral from negative a to a is going to be 0. And that's because these are going to be equal, but one area is negative and one area is positive. So they cancel out. So if you see that in an odd function, you can just jump that straight to 0. So kind of going through a few examples of some of these questions and how these might look, we're given that the integral from 0 to 3 of f of x dx is 6, and the integral from 3 to 7 of f of x dx is negative 8. And we're going to try to use these properties to define this. If you guys want to pause the video and try some of these on your own, it would actually be really good practice. It's kind of like problem solving and critical thinking skills. So I would highly recommend you pause the video and just look at the properties and just see if you can figure it out on your own. And then finish the video and watch for the answers and the explanations. So our first one, what we'll notice is that the 0 and the 3 are flipped from that first integral. So we had 6. When we flip the integral, that flips our answer, and so we're going to get negative 6. Okay, the next one's a little bit trickier because we have from 0 to 7, and we never had that. But we want to kind of think about is we need an integral that starts off with 0 and then goes to some other value because we don't have 0 to 7. So we do have 0 to 3. And so then if we end at 3, then we need to start at 3. So then we need an integral that starts at 3. And we have one that does go up to 7. And so that's kind of how I like to think of that, is I always start here, and I see what integral do I have that has a 0 in it? And then I use that integral. And then from there, you just kind of think, okay, now I have a 3. What integral do I have that starts at 3? Okay, so this would be 6 plus negative 8. And so we end up with negative 2. All right, our next one, integral from 3 to 3 f of x, should be very easy, just automatically 0. As soon as you see the same endpoints, we have 0. All right, and then our next one, we have this 3 in here. So what we can do first, if we really want to, is we can pull out the 3. And we have the integral, so 3 times the integral from 7 to 3 of f of x dx. And then what we'll notice is up here we have the integral from 3 to 7, but if we flip our endpoints, that's going to flip. So, if we really want to show our work, we can do this. But if you had just said, 3 times negative 8, that would have worked as well. So negative 3 times negative 8, we end up with positive 24. So again, you could have showed this step slightly differently. But as long as we get positive 24, we'll be okay with that one. All right, our next one is a little bit tricky, and that's when we have this, 2 plus. And a lot of students get really confused here, and they just stop. And this is kind of one of the one times where you really would want to do that separation rule. So whenever we see a plus, we know that's a separator. So this is the integral from 3 to 7 of 2 dx plus the integral from 3 to 7 of 3 f of x dx. So the integral from 3 to 7 of 2, right? Well, we need to actually take this integral. So the integral of 2 is 2x from 3 to 7. But then the plus, now here the integral from 3 to 7, we know is negative 8. So this is just going to be 3 times negative 8. Right? If you wanted to pull the 3 out, you can. If you want to just kind of think of it in your head, that's fine too. So here we need to do 2 times 7 is 14, minus 2 times 3 is 6, and then minus 24. So that'll give us 8, right? 14 minus 6 is 8. 8 minus 24 is negative 16. Okay, our next one is asking us for the integral from negative 3 to 3 if we know that f of x is even. So if we know that f of x is even, right, like even symmetry, then we know that we'll have the integral from negative 3 to 3 being double the integral from 0 to 3. So this is just going to be 2 times the integral from 0 to 3 of f of x dx. And we knew that that integral from 0 to 3 was 6. So 2 times 6, and we get 12. And then if it's an odd function, then we know it's just going to be 0. Now, I do want to add one more question on here just to kind of help us and to practice. And so this is actually going to be a very, very tricky question. So I'm giving you one new integral, and we're saying the integral from 5 to 7 of f of x dx is 3. And we want to know what is the integral from 0 to 5. So this is tricky, but I'm going to show you the method that I use. So I know I need my first integral to start off with 0. So I want an integral that starts off with 0. And the only one that I have that has 0 in it is from 0 to 3. So I'm going to say the integral from 0 to 3 of f of x dx. Now I can add on an integral that starts off at 3. Well, the only integral that I have that starts off with 3 is that 3 to 7. So the integral from 3 to 7 of f of x dx. Now I've gone from 0 to 7, but I want to end up at 5. So now I'm at 7. What other integral do I have that starts off at 7? I don't have an integral that starts at 7, but we do have this integral with 7 in it, and you can always flip it. So I'm just going to say plus the integral from 7 to 5 of f of x dx. And now this would be the same as the integral from 0 to 5 of f of x dx. And the reason for that is we started off at 0. We can kind of cancel out the 3's, kind of cancel out the 7's, and we're ending at 5. So that's the same as that integral from 0 to 5. Now, when we plug these in, we do need to be careful about if we flipped any of them, right? So the integral from 0 to 3 we were given was 6, and the integral from 3 to 7 we were given was negative 8. But we were given the integral from 5 to 7. This one we flipped, so this is going to be negative 3, not 3, because we had flipped our endpoints. So that's 6 minus 8 is negative 2, minus 3 is negative 5. So that's a little bit more of a challenging one, but it's something that we may be expected, and that's kind of that process of doing those more challenging ones. Okay, this next one we're going to do with a graph and kind of go over some of those even and odd rules and just that geometry a little more in detail. So our first question is, what is the value of the integral from 0 to 3? And on the AP test, they will give you some of these semicircles and some quarter circles. So just kind of remembering that we know that the area, there we go, the area of a circle is pi r squared. So we need to kind of, in doing that, the area of a semicircle would be 1/2 pi r squared. And the area of a quarter circle would be 1/4 pi r squared. So that's something to just kind of watch out for. So as we start this problem, we're going to start at 0. We're going to end up at 3. So I'm going to break this up into shapes. Okay, I have a triangle, I have a rectangle, and then we have basically a quarter circle. So we can kind of do those one at a time. So I'm going to say the area of the, basically like quarter circle is 1/4 pi times, now the radius of this quarter circle is 2, right? 1, 2, or 1, 2. So that radius is 2. So 1/4 times pi times 2 squared. 2 squared is 4. 4 times 4 cancels out. So we get pi. The area of the rectangle is 2 times 1, right? Width of 2, height of 1. So we get 2. And then the area of the triangle is 1/2 times the width is 1 times the height is 1. So it's 1/2. And we're going to add all of those up. So that value of our integral is equal to basically pi plus 2 plus 1/2, or pi plus 5/2. And that's kind of how you do that. You could also number these, like instead of using the pictures like that, sometimes I'll just give them numbers. I'll say like the area of region 1, region 2, and region 3. Then just call this like region 1, region 2, and region 3, and do something like that. Okay, our next one, what is the value of the integral from 0 to 4? And if we notice the symmetry, we don't actually have to redo any of our work. We can just kind of say, hey, well, the area of 4, like this fourth region, those are going to cancel out, right? Because they're opposite. So if I went from 0 all the way to 4, I know that those two triangle areas are going to cancel out. And so we could just say that it's pi plus 2, right? Because we really only need regions 1 and 2 now. And so that's something kind of neat as that little trick, that symmetry trick. Okay, you also could have set something up, maybe like the integral from 0 to 3 of f of x dx plus the integral from 3 to 4 of f of x dx equals the integral from 0 to 4 and set it up that way. But, I think that's more work than just kind of looking at the graph and seeing that those two regions would cancel out. Okay, our next one, what is the value from -3 to 3? So from -3 to 3, what we can see again is we can see more symmetry. So we can see that this is that even symmetry where this whole left side is the same as the right side. So this would be equal to 2 times our integral from 0 to 3, which was pi plus 5/2. So that's 2 pi plus 5 when we distribute the 2. Right, 10/2 is just 5 or cancel out the 2's. Right, and then these last two questions are very, very important. They're applications of that fundamental theorem of calculus. And it's a very important concept for us to make sure that we understand. And so this first one says, if big F of 0 is 5, what is the value of big F of 3, where big F is the antiderivative of f of x? And so what we want to do is the 0 and the 3, those are x values. We want to realize that on the graph, when we were doing these areas, we're always using the x values for our endpoints. So we want to kind of start to realize that these endpoints are always our x values. And so when we see this 0 and 3, we're going to set this up as an integral from 0 to 3 of f of x dx. And then by the fundamental theorem of calculus, we can say this is equal to big F of 3 minus big F of 0. So anytime we're given something like this, we want to jump to that FTC, and we want to write this line here. This line is super, 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 super important to make sure we can do. Now on the left side, you're actually going to, because we don't know the value of f of 3, we cannot plug this in. That's what we're solving for. So that means we need to evaluate the integral, and we need to evaluate the other endpoint. And so the other endpoint they gave us, so we know this is going to be f of 3 minus 5. The integral we can just do from the graph, or we can, if we had an equation, we could do it from the equation. But we have a graph, so we'll do it from the graph. And we actually already did this in the first part, and we got pi plus 5/2. So we'll just add 5 to both sides. And right, times 2, we get 10 over 2. And so this will end up being pi plus 15/2. And that'll be our answer for f of 3. So again, this is a very, very, very important question. It is almost guaranteed to appear on your free response, is this fundamental theorem of calculus topic. Okay, so we'll try one more. If f of -2 is equal to -2, what is the value of f of +2? So we're going to kind of do that same setup. So the integral from -2 to +2, because we're going to take our x values, of f of x dx will be equal to big F of 2 minus big F of -2. That's the fundamental theorem of calculus. Now, when we look at this graph, we can actually see that symmetry. And so that can help you out a little bit, is we can see that this is symmetrical. So we're going to know that the left half would have to equal the right half. And so that can help you out. Or you can just, make it one big one, and that's fine as well. I'm going to just do it as one big one. So I'm going to call this region 1 and this region 2. Now this is a half circle, not a semicircle. The radius, though, of a half circle is just half of it. So the radius is 2. Okay, so kind of the area from my number 1 is 1/2 times pi times 2 squared. And that's going to be 2 pi, right? 4 times a half is 2. And the area of that rectangle has a width of 4 and a height of 1. So 4 times 1, and we get 4. So we have 2 pi plus 4 is equal to, right, 2 pi plus 4 is that integral. F of 2 we don't know yet. Minus f of -2, the answer was -2. So that's 2 pi plus 4 equals f of 2 plus 2. Subtract 2 to both sides. And we get 2 pi plus 2 equals to f of 2. All right, so again, kind of same concept, not too bad. And when we look at the homework associated with this, It's our day 50 homework. The first few questions look like those first examples we did where they give us two starting integrals and then we have to kind of combine our properties. Number 6 is a little bit tricky, but on number 6, just realize that when we're doing these multiplying and these dividing properties, they will work that same way. So, this is 1/2, and you can pull out the 1/2. And so that's something that, it's a little tricky, but I think you guys can figure that out. And then 5, 6, and 7, again, are just another take on that. And then over here, we're given a graph, so it's similar to the problems that we just did. And then these last two, we're given f of -2 equals 5, so that's where we're going to need to apply that fundamental theorem of calculus. Okay. There is also this 2003 AP Calc problem number 4, and then a 1998 problem, and a 1999 problem. So there are those 3 AP style questions. These are not going to be part of your day 50 homework, but what I will do is that those 3 AP questions, they'll be very good studying for your final, and I will make them extra credit. I will post the answer keys for them. So I'd prefer that you don't just copy the answers, but that you attempt them first, maybe in like pencil, and then grade your answers in pen. And you can even use the point breakdown to try to give yourself a score out of 9. And I'll give you extra credit if you do that. I want to kind of see maybe your work in pencil and then your grading in pen to give you that extra credit. I don't want to see that you just copied everything, right? Like no one's going to get a perfect score in all 3 of these the first time. So that'll be for extra credit.